Assalamualaikum warahmatullahi wabarakatuh, and good morning. I hope you guys can hear me. Can you hear me?
Yes, doctor. Good morning.
Morning. Thank you. So right now, how many students do we have? Based on the attendance, there are only 39 out of 52. Okay, we'll give it a few more minutes. In the meantime, have I mentioned to Guy have I mentioned anything at all about test 2? When is it supposed to be? No, I haven't. Okay, your test 2 is going to be covering the topic on distillation and also liquid extraction. I'm not sure whether Dr. Noshikin did mention anything about the date. Did I post it in our group?
I think for 4th January.
4th of January, yeah, that's I think that's the date, yes. So that's about 2 months from today. Today is already the 2nd. So we need to finish distillation. Distillation is quite a long topic on itself. And the test will only cover binary distillation. It will not cover multi-component because multi-component is for the final. So and then there's another topic that is the liquid extraction. Liquid extraction. I'm not sure I will have enough time or not to cover everything before the test. Because we only have we have one test. Next week is a break, semester break. We haven't even look at, I think we can finish binary distillation in 2 weeks' time. Inshallah, we will be able to complete everything before the test. But whether we'll be able to complete multi-component distillation, I'm not sure. I'm not too sure on that. Okay, so anyway, let's see how many. Okay, there's 46 of you guys already. That's about test 1. Test 1, question 1, the question number 1 was said by Dr. Manzura. It's actually set by Dr. Manzura. So she will be marking on that. She realized that she did make a mistake. So she will correct according to the steps that you have done. Yeah. She got it right until, well, I think that the problem is the overall heat transfer coefficient, the overall mass transfer coefficient. I think that's the problem. Anyway, she said she marked it according to the methods, the correct methods in solving it. Anyway, the second question is set by me. That's almost similar to your assignment, question 2, for the tray tower. But unfortunately, most of you guys don't have enough time to do it. Dr. Mazura, the lecturers earlier during the morning, when they got a copy of the question, they don't want to have the graph included, the ready plotted graph included. Reason is because they said there are some students that don't have printer and some students that, just that be unfair. So I accept that argument. So we decided not to have the graph, not to include it, but somehow when Dr. Mazura posted the latest version of the test 1, she accidentally included it. Not accidentally, she said she deleted it, but it was not deleted. So it's at the end of the last page, of the questions. I will be accepting those that use the graph, but I will penalize the student that use the graph because the instruction was to use the equilibrium data. Okay, so those that use the graph will be penalized, not much. Your working will be accepted, but in terms of not following instruction, because the instruction was supposed to be using the equilibrium data, that means you need to plot it. So I'll accept those that did it using the ready plotted graph, but I will penalize, I will deduct a few points out of it. Yep. Okay, it's already 11:06, so I will stop this sharing the QR code. Okay, we will look at a single stage equilibrium contactor. As we have seen before, when we were looking at absorption, a single stage contactor is not really suitable because there's not much mass transfer going on. But this is a good start for you to understand what is going on. So if you look at this diagram, you have vapor coming in at V2, that's the flow rate, and liquid is coming in having a flow rate of L subscript 0. The composition, as always, when it is vapor, you denoted the mole fraction by Y, and when you have liquid, the mole fraction is X. Over here, we have the subscript A, because you have component A, that's the lower boiling point component, and you have another component B, which is the higher boiling point component. So we'll be concentrating mainly on component A, the one that is the lower boiling point. So the subscript for your mole fraction will be mainly for component A. And this is your first stage. So any flow rate, any stream that is coming out from that stage will have subscript 1. For example, V1, L1. Yeah, so the mole fractions for the vapor and the liquid will follow suit. So you will also have 1 as the subscript for your mole fraction. Yeah, so there's a new term that there's something you need to assume. You need to assume a constant molar overflow. Constant molar means if you're looking at the flow rate of the vapor flow rate will be the same. It doesn't change, it's constant. Same goes for the liquid. The flow rate of the liquid will be the same. That is the assumption make. Okay. So we'll be looking at a single, in this case, we are looking at a single stage and you only have two components. Yeah, so you do the meter balance as always. You have the input equals to output. There's no reaction here, just separation. Your input is coming in here, that's the liquid, and that's the gas. Okay, so that's the input, and the output is coming out here. That's the liquid coming out, and that's the gas coming out. So input equals to output, and when you do the meter balance on the component A only, so you will be putting in the mole fraction. Okay, that's the equation. How to get the composition of your outlet stream, you have to do it using graphical method. Okay? So let's look at one example. Of course, you need to know the equation, which is the material balance on component A also, beside the graph. But here we have an example. The author of this textbook uses a lot of examples on benzene and toluene. Benzene and toluene is an ideal mixture. So somehow there's a lot of example in this textbook using benzene and toluene. So over here we have a mixture of benzene, which is the light, the component with the lower boiling point, and toluene is the component with the higher boiling point. And you have a mixture that contains 0.4 mole fraction of benzene coming in. That is the vapor coming in. So your vapor coming in has that mole fraction. That is for benzene. And the flow rate of that vapor is 100 kilogram mole. I would like to point out that the flow rate, when you're dealing with absorption, when you're dealing with distillation, so far, the flow rate that they are in molar flow rate. Okay, so the unit is in kilomole or mole or pound mole. So do take note of that. So your vapor coming, the flow rate is 100 kilomole per hour. This is the pressure of your system. And that vapor will be contacted with 110 kilogram mole of a liquid at its boiling point. So the liquid coming in is 110 kilomole per hour. And another thing that I would like to point out is that your vapor is at its dew point and your liquid is at its bubble point or boiling point. And so this two stream is, for the vapor, it is at the dew point, and for the liquid, it is at the boiling point. That's what actually happened in the column, in your distillation column. Okay? So they are contacted in a single stage. That means that is equivalent to one tray. The stream is contacted long enough that the vapor and the liquid will come into equilibrium. Okay, so in this example, you're supposed to calculate the flow rate, the outlet flow rate, and the compositions. So that means you need to find the flow rate of your gas and the flow rate of your liquid plus the mole fractions for, of course, for benzene. If you know benzene, you know the rest will be for toluene. So how to do it? You need your material balance. So I'm going to copy my material balance from the previous slide. We do know the mole fraction, or not, sorry, the mole fraction, of course, we do know the input, the stream coming in, the mole fraction, we do know that. And also we do know the flow rate of the inlet stream. So let's substitute in the values that we have. I'm not going to write the subscript A because it is understood that we are referring to component A, which is in this case benzene. So that's your equation. And as you can see, you have 4 unknowns based on that equation, 4 unknowns. But there's another statement in the statement in the equation that states you will assume constant molar overflow. And with that assumption, you will assume that L1 is equals to L subscript 0, V1 is equals to V2. Okay, so that means this flow rate is going to be the same as that flow rate, and that flow rate is going to be the same as that flow rate. So for your liquid flow rate, it is 110 kilomole. I think that is kilomole, not per hour. It's just kilomole. and your vapor, the flow rate is 100 kilomole. Now, when you rewrite this meter balance, you are left with only two unknowns. Need the bracket. Two unknowns, one equation, not enough information for you to solve it. So you need another, you need extra information. So the extra information is in the form of our graph. Yeah, so let me try to get the graph. We need the benzene toluene graph. So let me try to get this, copy it. There you go. Try to fit everything in here. Okay. This is our graph for benzene and toluene. I need to erase this. So what we need to do, or you need to do, I'm assuming that the second test also you need to plot yourself your graph, hand plotted, unless they decided that the graph will be ready plotted. If it's ready plotted, then we will give it a few, maybe one day before for you to be able to print it. I hope that that can be done, but I can't guarantee. So just know how to plot your graph. The graph is plotted whereby the x is your x-axis, that is the mole fraction of component A in the liquid, and the y-axis is the mole fraction of your component A in the vapor. So this is your equilibrium curve. That's your equilibrium line or your curve, and you can get it from the appendix. Therefore, in our case, it's already I already show you guys the based on Rao's law how it can be obtained, but in fact you don't really need Rao's law, because over here in the table 1111, you have your x there and your y there. So you can just plot it based on these values, and you will come up with your graph, which is for an ideal solution. You get a perfect curve. In this case. And so what you have to do next is to draw your 45-degree line. I did mention that your 45-degree line is supposed to, for you to compare how easy it is to plot to separate your components. Trying to get a straight line. There we go. Okay, that is our 45-degree line. Now, equations. Let's look at the equation. You have the composition. You need to calculate the amount. We already done that. We already have L. You have already L1. You already have V1. Okay. So now, in order to get your X1 and Y1, it has to be done by try and error. You look at your graph over here. Let me get my graph. Okay, by try and error, try to get points, maybe 3 or 4 or 2. I think we need at least 3 points using this equation. Let's say x1 equals to 0.2. Then from there, you try to get your y1. So let's put in the values. 110. I'm going to just multiply the values that I do have. That will be easier. That is 33 plus 40 equals to 110 times by 0.2 because I substitute the x1 equals to 0.2 inside the equation. So now I have 100 y1. So from there, I should be able to get my y1. So 110 times by 0.2, that's 22. So let's calculate what is our y1. Y1 is equal to 0.51. So I will locate that point on the graph when my x is equals to 0.2, my y1 is equals to 0.51. So 0.2 is there, 0.51. This is somewhere here. 1. So that's 1 point. It's not on the equilibrium curve, so that's not the point that we want. The value of x1, and y1, it should be in equilibrium because we said that the system comes to equilibrium. Okay, so your x1 and your y1 should be in equilibrium. The composition of your x1 and your y1 should be in equilibrium. So it should be on the equilibrium curve. But our first point is not on the equilibrium curve, so we need to get a few more points in order to whether we get to get a straight line. Then where that straight line intersects with the equilibrium curve is your value of x1 and y1. So let's get another point for x. Let it be 0.3. So your y1 will be what? So substituting in the values inside the equation, substituting x1, that's 0.3, get 100 y1. So if you do the calculation, y1 is equals to, that turned out to be 33. So 33 cancel off. Yeah, so obviously y1 is 0.4. Just by looking at the equation, just you cancel off the 33 on the left hand side and 33 on the right hand side. So you have 40 on the left hand side and you have 100 y1. So y1 is equal to 0.4. So let's put that value over here. So our x is 0.3, our y is 0.4. That's 0.3 and 0.4 is there. Again, it's not on the equilibrium line. To me, this is good enough. 2 points is good enough for you to proceed to draw your straight line because a straight line just needs 2 points. But the textbook, the solution in the textbook did extra. The author did extra. The author continue with another point. So I'll just show you guys. Okay, 0.4. Let's the other point be 0.4, and what will be y1? Let's do the calculation again. 33 plus 40 equals to 110, 0.4 plus 100 y1. That is equal to 44. That's 0.29. Okay, so your y1 is 0.29. For 0.4x, 0.4 is 0.29. 0.4 there, 0.29 will be somewhere there. So you will join these 3 points, connect them up using a straight line. So let's do it using red color. Let's draw a red color line. Guys, I have my straight line. So where is my yx and y1 is on the equilibrium curve. So if you project this, let's do a dotted line. So if you project it where the intersection with the equilibrium curve is, that's not a straight line. that is my value for x1 from the x-axis, and the corresponding value for my y that will be from the y-axis. So if we look at the value for x1, that's 2, 4, is almost 6. It's almost 0.26. About the composition of x1 is about 0.2, so not 6, 2, 4, 6, yeah, 6. So about 0.258 maybe, roughly estimate. It's just a rough estimate. And the y value, if you look at the y value, that's 2, that's 4, that's about 4, 5. That is your y1, and your x1 is 0.258. But the solution from the textbook, let's have a look at the solution from the textbook. Okay, the textbook y1 is equal to 0.455, and the x1 is 0.25. So, well, it's not exactly the same, because it's how we draw our lines, how we read off the values that will contribute to the change, the difference. Any questions? This is a single stage, and if you can see, your x initially is coming in having this composition. Now your x from my graph is 0.258. So that's the new equilibrium composition for my liquid. Whereas for my gas, I got 0.45 initially. If I draw this, initially coming in, the composition of my Y2, what is that composition? Is 0.4. So now you can compare that there's not much change in the composition there. Okay. Same thing for the gas, for the liquid, 0.3 going to 0.258. It's only a slight, very small change. So a single stage is not good enough for the industry. You need, in order to achieve bigger changes, you need more than one stage. Okay, any questions?
Doctor,
No.
For the graph, is it certainly a straight line if you do the try error and you connect all the points?
Yes. Because it's based on the material balance. You will get a straight line.
Thank you, Doctor.
You're welcome. Any other questions? Normally, when you plot the graph, you will get the maximum mole fraction is always 1. 1. You will get maximum 1. So that you can draw your 45-degree line. Just connect the 0 to the upper point, which is 1. So you will know that your 45-degree line is connecting from the origin to the upper corner of your graph. And so normally you will plot it until 1. So no questions? Okay, we have a few more simple distillation. They are mainly single stage. The other one here is equilibrium or flash distillation. Again, the product will be in equilibrium. And if you look at the diagram here, you have your feed coming in, having that composition, preheated in a heat exchanger. When it is preheated, that means your feed become hotter. After that, it passes through a pressure reducing valve, meaning your feed will be, the pressure will be reduced. The pressure will be reduced from the initial pressure. there will be a drop in pressure. So initially it is a high pressure, now there's a drop in pressure. And when the drop in pressure occur, what happens is that your liquid initially is in a liquid, your feed is initially in a liquid phase. So when there's a sudden drop in pressure, your liquid will vaporize. Yeah, your liquid will vaporize, but in doing the vaporization, the sudden vaporization will cause a drop in the temperature. And when there's a drop in temperature, the higher melting point component will condense. Because remember, you have two components. We're talking about two components, A and B. Your component A is the lower boiling point, and this B will be the higher boiling point. So when there's a drop in temperature, component B will start to condense. Initially, you have your feed in a liquid phase, and then you drop the pressure. When that happens, the liquid will vaporize. But in doing so, in vaporizing at the lower pressure, the temperature will drop. And when the temperature drops, some of the vapor will condense. And these are the ones that have the higher boiling point. The component that condense will be component B because it has the higher boiling point. So when the pressure drops, it will change from vapor to liquid. So when it enters the flash column, this is your flash column. Actually, it's just a simple drum. You will have liquid at the bottom, which is the condensed part, and you have the vapor at the top of that flash drum, because that is where it initially changes from liquid to vapor. And the vapor is mainly consists of the lower boiling point component, which is mainly of component A. But it's not totally A, because it's not pure A. There will be some B maybe inside. There will be some B in there, but not all of it will be pure A. Okay, so this is how a flash distillation works. You need to preheat your feed, which is in a liquid phase. Then you have to reduce the pressure using a pressure reducing valve. When it enters the flash drum, the vapor and the liquid will have enough time to come to equilibrium. You let it be in contact that both of the liquid and the vapor will come into equilibrium. After that, you get your product, which is the top product, your vapor, and your bottom product, your liquid, having that mole fraction. So this is the total balance. Your first equation is the total balance. Coming in, input is your F. Your output, you have two streams coming out. Your output, they are the vapor and the liquid phase. Over here, you have component A listed only for component A. The ventral balance is done for component A. Right, so we introduce this term F. F is the molar fraction of the feed that vaporized. That vaporized. So that means F is equal to V divided by F. The amount of vapor that vaporized, the molar flow rate, the molar flow rate of the vapor divided by the feed flow rate. So that is your V. That's the ratio. Yeah. So F is there. So when you divided everything by F, so this part becomes 1. So you end up with the second equation. So V over F is your F. That's how you come with the second equation. I'm going to tidy this up. And based on the second equation, you should be able to use. You're going to use that second equation to solve the unknown composition, which is the outlet composition. Again, you need to use your graph. You cannot solve it just based on one equation, because you have two unknowns. You have two unknowns. You have the y and you have the x. So you cannot solve it just only one based on one equation. So you have to solve it graphically, just like what we did in this example. Same thing as how we did it in this example. So you're going to do it the same thing. but in this case, you will be using this equation. Let's. I don't think there is an example here, but let's look at, maybe just give you a rough idea of how it can be done. I'm going to give you an example, just a rough idea. Let's say we have our feed is the flow rate is 100 mol per hour. Just give it per hour, or it might not be in. Okay, just that be your basis. Just let that be your basis. Your XF, it will be given because your XF is the feed, the composition of your feed that is normally given. So let's say it's 0.5 mol per mol. Okay, we have component A and B. So the amount that vaporized will be mentioned in the question. So for example, let's say you have the amount that vaporized is given, say 60 mol per hour, what you get. So your V over your F is going to be your F, right? That is going to be 60 over 100. It's going to be 0.6. That information you have. And you can get the flow rate of your L, the liquid, because you can get that from your meter balance. That's 100 equals to your vapor, that's your liquid. So you should be able to get the flow rate of your liquid. Okay, not kilo, it should be mol. So now, how to solve for your unknowns composition? You have to plot yourself your graph. Plot myself a graph here. Okay, let's draw. This is XA, this is YA. Our 45-degree line. That is our equilibrium line. So where do we start? We start at the value of XF. Right? So for example, this is my XF. So that's my XF, 0.5. So now what I have to do is, based on this equation, that equation, I will write that equation over here. 0.5 equals to my my F molar fraction that vaporized is 0.6 Y plus 1 minus 0.6 X. So this part will be, of course, 0.4. But again, you have one equation, two unknowns. So you have to do it by trial and error. Let's X equals to, for example, 0.2. Then solve for your corresponding Y. And then do the same thing for another point. For example, 0.3. Then get your corresponding Y. So now you have 2 points. So maybe just say roughly, you have 0.2 is somewhere here. For example, you get somewhere there. 0.3, you get somewhere there. Well, somewhere there. I think 1 point would be enough, I think. You don't really need to have 2 because you're going to join it and it's going to join that. Okay. Okay, it will join with that point here. It will join on the 45-degree line. So I think 1 point is good enough. You don't need to have 2 points because to draw a straight line, you need only 1 point. Okay. I mean, sorry, to draw a straight line, you only need 2 points because the other point is obviously on the 45-degree line. So in order to draw a straight line, you need that point. But then if you want to get another extra line, obviously it's going to be on that same line. So now you will get your outlet composition for your X there. That is your XA and your Y over here, YA. And so that's how you do your flash distillation. It's almost the same as the previous example, except that now you are looking at a different equation. Any questions? Any questions? Okay, no questions. There's an question at the back of your chapter, of this chapter, the chapter 10, which it's a good idea for you to try and do it. Practice on getting the value of your XA and YA based on this flash distillation. Excuse me. Okay, now there's another simple batch distillation. Actually, these are just introduction. The main topic is how to do multi-stage distillation. So we haven't come yet to that topic yet. We are just warming up now. And so this is a simple batch distillation. And if you look at the diagram, here you have your pot or your still. You put it inside there because it's batch. You know, batch means you put your profit at the beginning, and then as towards the end, then you will stop it. Okay, you get your product. So what happened here is that you put your feed into the still. This is the explanation, or the heated kettle. Okay, initially you put your feed there, your liquid there, and the initial amount that you put there is initial amount is L1. That's the amount you put inside the kettle. Okay, with that composition X1. That's the initial composition of your feed, which is denoted by L1 instead of F. And this is the amount that you put in. After you start boiling it, okay, so part of the liquid will vaporize and will be collected in the somewhere here after it have condenses. Then you have this heat exchanger there. So the first batch that vaporize, the first stream, the first vapor that condense and get collected in your vessel will be the richest in component A. Why is it richest in component A? Because component A is the lower boiling point. So the first batch that vaporize will have the most of component A. Excuse me. But as you continue to boil, more and more of component B will start to vaporize because the temperature now is getting higher and higher. Okay, so now your mixture over here will be containing component A and B. It's no longer just pure A. Okay. So the amount that is left in your kettle or the still is L2. Excuse me. Okay. L2 is the amount that is left in the kettle or the still. The composition now is X2. So what you need to find is the amount of the composition of the final of the liquid, final composition of the liquid, and the composition of your collected condensed vapor, which is in this case the one that collected over here. It will have an average value because remember the there's a mixture of A and B there. Why is it average? Because the first batch that vaporized is richer in A, but as more and more get vaporized, it gets more and more B. So you will get an average. So how to solve it? You will use this equation. You will know the initial feed and the composition. The final amount of liquid left, you will know, but you don't know that composition and you don't know the the amount the mole fraction of your vapor. So if you look at this equation, this part is an integral, and as always, it's either you can do it graphically or analytically. Yeah. So if you do it graphically, you have to plot x versus 1 over y minus x. There's a y minus sign there missing. And the area under the graph, the first x is going to be your x1. So your x1 is here. Let me scroll up so that we can look at the graph. Sorry, x1 is over here. X1 is over there. Why is x1 higher value? Because as more and more vaporized, we are looking at component A, guys. This is component A. That is A and A. So as more and more vaporized, I need to correct that. As more and more vaporized, there will be less of component A in your still. There will be less of A here in this still, in the liquid. Because more and more of A will be vaporizing. So towards the end, the mole fraction of A will be less. Initially, it's higher. So x1 will be here, x2 will be there. But the problem is, you don't know what is x2. You only know what is x1. So you have that value known, but you don't know that value. So it's by a trial and error. You got to get the area under the curve so that the area under the curve will be equal to that value calculated based on your natural log. Whatever that value, that will be the answer, that will give you your answer for x2. So the area under the graph should be equal to the calculated value of this equation on the left side. So it's by trial and error. So let's look at this example. Over here you have your L1. Your L1 coming in. It's not coming in, it's the L1 that you initially put into your kettle. And the composition of your L1 is 50%. That's that's x1. 0.5. L1 is equal to 100. So your component A is this N-pentane, and the other component N-heptane. Going to vaporize it until you get 40 mole is distilled. 40 mole are distilled. That means is that V or is it L? Distilled. Is that V for the 40? Is it V or is it L? Guys, 40 mole is distilled. Is that V or is it L?
L.
L. Because your L is the one that is left in the column. The V is the one that is at the top, the one that get collected. Which one? Anybody? Is that the amount? Is 40 mole? Is that your until 40 is distilled? Is that your V or the L that is left in your kettle? What is it? Distill. Got to understand the statement. Distill. So is that your V or is that your L? V. V. It should be going upward. It is distill, isn't it? It should be the one that is getting into the vapor, that is going up as the vapor. That is 40. So if 40 is distilled, that means the amount left in the kettle, if this is 40, the amount left in the kettle will be, initially is 100. initially L1 is 100. That is initially in the kettle. So when 40 mol is already distilled, it's not the second. 40 mol already distilled. So what's left in the kettle? Guys?
60 more of L2.
60. That's left. Initially it's 100. 100 mol. Okay? So 40 is the amount that is distilled. So the statement distilled means that it is vaporized. Okay? So V distilled, so your L1 already brought it there. So let's put it over here. Your X1 is equal to 0.5. Your L2 is the amount that is left in the kettle. So that's going to be 60. So the question is, what is the average composition of your vapor? And distill, again, you have that statement, distill. So you need to get your understanding correct here. Distill means that it is becoming vapor, yeah? That it changes into vapor. So your vapor is, the question asks for the average composition of your vapor and the composition that is left. The composition that is left, that is the X2 that is left. You need to find these two values. So over here you have your X and Y data for your system, and pentane and heptane. So you should be able to plot your graph. So you're not going to plot Y versus X or X versus Y. Why? Because based on the equation over here, you're supposed to plot X and 1 over, you're supposed to plot this graph. Let's get the equation. Going to use that equation to solve this problem because this is a batch distillation. So putting in the values, L1 100, L2 60, X1 2.5, X2. That's, if you do the calculation, 0.51. So your area under the graph must be equal to 0.51. Must be equal to 0.51. So you need to find that X2 value so that the area under the graph is equal to 0.51. So it's just by try and error. You need to plot it based on the data here. Or you can use it, you can do it numerically like we did for cooling tower. You have your X, you have your Y. You need to Y minus X. 1 over Y minus X. Get your delta X, because the graph is in this format. Okay, get your delta X. Then get your 1 over Y minus X average. Lastly, multiply the two of them. The sum should be that value. So when is it 0.51? That's the X that you need. You need to do it until the summation is equal to 0.51. And that will give you your X2. And that's how it's done. Either you do it graphically, and if you do it graphically, then it will be something like this. Or if you do it numerically, that's how you're going to need these few data to do the calculation until you get 0.51 as your summation for the last column. So next part of the question asks for the average composition of your vapor, and that can be done using the last this equation. You can do that using this equation. So when we plug in the values, we have 100, 0.5, 60. The value that you get from your graph just now or from your numerical method, that value should be known by now. By now, you should know that value. So L1 minus L2, L1 is 100, L2 is 60. So the only unknown left is your vapor composition. That's the only unknown left. So you should be able to calculate it now. So let's look at the solution. Over here, the graph has been plotted, and it so happened that the value of x2 is 0.277 to give you the area under the curve 0.51. The area under the curve should be 0.51. That's when x2 is the correct value. Okay, so with that information, you substitute it inside the equation here. You have your x2 there. So you should be able to get the answer for your vapor composition, which is 0.835. That is the composition is for component A. Initially, in your problem, this is the composition of A in the mixture coming in the kettle. This is the amount. But once you do the distillation, you have a higher amount of component A in your vapor that condense. So that is a big difference from the original composition of 0.5. That is actually what we want in distillation, because we want to change the composition from a low value to a higher value. So the higher value is the one that is being distilled, the one that changes into vapor and then condense and get collected. Okay, guys, any questions? For so far, the three cases that we look at, they involve trial and error. You have to plot your graph. You have to draw. You need to get certain points. Draw your straight line, and for this example, you need to plot your graph and get the area under the curve, and find the value of x2 when the area under the curve is equal to the solution of the integral, or the solution on the left hand side of the equation. So for this example, this is the equation. Any questions? You have a lot of problem at the back of the chapter that you can try to test your understanding, how to solve the problem. Any questions? No question, I assume, because nobody is asking. Okay. Almost 12. Okay, we got another roughly 50 minutes, 55 minutes. Simple steam distillation. I'm not going to go through this. I'm just going to briefly explain it. Steam distillation is mainly used when you have a very high boiling point substance, that need to be boiled, need to be distilled, but you cannot distill it at a very high temperature. Because if you distill it at a very high temperature, you will decompose it. You can't afford to distill it at a very high temperature, but because that component itself will decompose at a high temperature. So you need to do the distillation at a much lower temperature. Most of the time, steam distillation deals with product of plants. For example, getting essential oil. So you cannot distill it at very high temperature, because if it's too high, you will decompose the substance. So what you do is you put in steam together with your liquid that you want to distill. So the steam will bubble through your liquid mixture, Yeah, and when the steam bubble through, it will bring along when it flow upwards, it will bring along that substance that is the one that the higher boiling point substance. It will bring along it. It's as if it carry it with the steam carry it along. Yeah, and then when it condense, you will have your oil plus the steam. You will have when it's condensed, you will have your oil plus water, because steam, when it condenses, it becomes water. So over here, that's water at the bottom, and that is your oil. Because the oil and the water, they cannot mix. It's immiscible. So when it is immiscible, you can easily spread the two. So this is the main step in steam distillation. Because in this diagram, you only have one stage. Normally, in the industry, you have more than one. So they do have steam distillation in the industry, but it is multi-stages. Yeah. So we'll not go too much through that, but the equation is, this is vapor pressure. Oops. That is the vapor pressure of component A plus the vapor pressure of component B. What is A? A is pure water. B is the component that you want to get the oil, for example. Okay? B is the component that you want to distill. Component A is your steam, your water. Okay? So the vapor pressure of the two of them add up will become the total pressure. And when you divided the mole of component B that distilled to the mole of component A that is also distilled, remember distill means it is the one that vaporized. That ratio is equal to the vapor pressure of B divided by the vapor pressure of A. That's the two equations that you need to know. Beside this equation, which is Rao's. I think it's Rao's or Dalton. I'm not sure. Is it Rao's or is it Dalton? You can check on that. And so these two equations are the equations that you will be looking at when you're dealing with steam distillation. So we will not do any example on this. There is a problem at the back of the chapter. Okay. So we will look at fractional or rectification distillation. This is the main topic that will be asked in your test 2. This is the main topic beside multi-component distillation. Yeah. This is what they use in the industry. You have multi-stages. You can look from the diagram, the schematic diagram. Over here, your feed is coming in the form of maybe liquid. Yeah. If your feed is in the form of vapor, it should be coming at the bottom. Yeah. If since your feed is coming somewhere along the column, so most of the time it is liquid. And you have in your column stages, that is the tray. You have your tray here. You also have a partial reboiler. That's a partial reboiler. Why is it mentioned partial reboiler? Because part of the liquid that enter that reboiler will be, part of it will vaporize, whereas the remaining will still stay as liquid. So that's a partial reboiler. Yeah. And you also have a condenser. The diagram, the way the diagram is drawn, this is a total condenser. You also have another type of condenser, which is partial condenser. When you have a total condenser, the vapor that enter that condenser, all of it will be condensed. So this is in the form of liquid. That the stream here is also in a system reflux. Reflux means what part of the vapor that is condensed will be returned back into the column. Part of it will be returned back into the column. And so you have this V there, the L there. The reflux ratio is always L over D, not V. There's two actually. There's two reflux ratio. One of it is L over B, and one of it is L over D. But most of this textbook will be looking at L over D. That's the reflux ratio. Okay, what else do I need? Okay, I need to mention that the section of your column that is above the fit, that is the rectifying section, or because in your textbook is referred to as an enriching section. Why is it referred to as enriching? Because the vapor, as it flows upward, will get enriched in component A, because you have only two components, A and B. So as the vapor goes upwards, it gets richer and richer in terms of component A. So it is enriching section. And the bottom of your feet, the section that is bottom of your feet, that is the stripping section. That is where the liquid coming down will get stripped or removed of component A. Yeah. The liquid, okay, is that correct? The liquid coming down will be stripped of component A, because as it goes down, the temperature gets higher towards the bottom of the column. As the liquid goes down, the bottom of the column is at a higher temperature. So component A is the lower boiling point component. So as the liquid goes down, component A will vaporize. So it is stripped of component A. So component A will start vaporizing upwards. So the liquid is being vaporized. The liquid now is stripped of component A. So when it enters the reboiler, part of the component will vaporize, and that's where this component is going upwards. The vapor is going upwards. The vapor is going upwards, and your liquid is going downwards. So the liquid is on the tray, and your vapor will pass through that liquid. That's where the mass transfer is occurring. Your liquid will come into equilibrium with your vapor, as is the case for a single stage. Earlier, when we were looking at a single stage, that is actually what is happening on a tray. This is the single stage. This is actually a single tray or a single stage. The vapor coming in is the vapor from the reboiler or from the bottom of the column. And the liquid coming in is the liquid that is written as reflux at the top of the column. So you have this vapor going upwards and the liquid going downwards in the column. So this is one tray. And the vapor and the liquid will be in direct contact on the tray. That's where the mass transfer is going to happen. And then you will get your liquid coming out of that tray in equilibrium with the vapor coming out of that tray. So this is equivalent to one tray or one stage. Okay? So, but now you'll be looking at multi-stages, you have lots of tray, not only one. And the function of the reflux is that you will get more and more pure product of your distillate. This is referred to as distillate. Not pure, almost pure, not pure. There's almost impossible to get 100% pure. Okay? And this is your bottom product. Okay? Denoted by the symbol W. Some textbook uses B because it's bottom, but our textbook that we are using uses the symbol W, and over here distillate, capital D. Okay? Your feed obviously F. Okay, so your bottom product will be most of it will be in terms of component B. Most of it is contain component B. Your distillate, most of it will contain component A. Because remember, A is the lower boiling point and B is the higher boiling point. So these are the two products that you will get from a fractionation column. Yeah. Unless you have multi-side stream, multi-product, then that's one you will look at it later on as one special case. Yeah, in this case, you want to get two products, the distillate and the bottom product. So how to do the problem? You will do it graphically using McCap-Thiel method. Yeah, I already explained this part. You will use McCap-Thiel method. You will draw your graph. So again, you have to solve the problem graphically. And you have to draw your graph. And the graph, your x-axis will be the mole fraction in liquid, x, denoted by x, and your mole fraction in vapor, denoted by y. Okay. This is your feed composition. This is your bottom composition. This is your distillate or your top composition, top product. You need to draw your Q line. You need to draw your enriching operating line. You need to draw that enriching operating line, and you need to draw your stripping operating line. You have 3 lines. And after that, you do your stages in order to get your number of theoretical stages. Theoretical, just like the way we did in absorption, you have to do the staging, the steps method. Normally, you start from XD. Your first stage will be the first step here. That is your first step, your first tray. Yeah? So how to go about it? Okay, again, you're going to, before we start looking at an example, we will look at the equation. This is your total balance. This is in terms of component A. I did not write the component A in the for the subscript because it is understood. I did not write subscript A there because it is understood we are looking at component A. We will assume, again, just like what we did in the single stage, equal molar flow. That means in this section, the liquid coming down is L is going to be the same as the L is going to be the same as the L. Okay, the vapor going up from this part and this vapor stream and that vapor stream will have the same molar flow rate. But if you go down towards the stripping section, this liquid coming down, let's give it a symbol. So let's this component N. That will be Ln minus 1. That will be Ln. Okay, Ln minus 1 will not be the same as Ln because it's not the same. You have two separate section here. Okay, for the enriching section, you have the same molar flow rate. For the stripping section, you have the same molar flow rate, but they are not the same between the two of them. Okay, so let's give this symbol again. This is N minus 1. Oh, this is not a good symbol. Let me undo that. Let me put numbers then. It's easier if I use numbers instead of alphabet. 1, 2, 3, 4, 5, 6. Yeah. So that stream L3, because it's coming down from stage 3. This vapor, V4, V3, V2, V1. So V1 is to V2. Equimolar flow rate, constant. L1, L2. Okay, here. L4, L5, L6. This is V7, V6, V5. Okay, V5, V7 is equals to V6 equals to V5. Your L4 equals to L5 equals to L6. your L here will not be the same as the L over here. They're not going to be the same. They're not going to be the same. Neither is the V over here going to be the same as the V in the enriching section. They're not going to be the same. But for this section only, they are the same. The V will be the same, the L will be the same. For the enriching section, the V will be the same flow rate, the L will have the same flow rate. It's just that if you are in the enriching section, you're not going to have the same flow rate as that in the stripping section. Yeah, so that's what the implication is. Oh, okay, now to do the graphical method, you need to plot your Y versus X plot. Your equilibrium data normally is given. For example, you have benzene and toluene, so this will be the plot for A, YA, and XA for benzene only. So if you're looking at benzene toluene, the data earlier, table 11.1-1. Okay, this is your benzene. For your X and your Y. For a pressure 1 atm. So plot your X versus your Y. And it will look something like this. Graph that, something like this. Okay. That is your X and your Y. Obviously, you will not get that line, of course, but this is for an example, for that example. Yeah. You will get your points, and that is where your equilibrium curve is going to be. From the points, you will get your equilibrium curve. You need to draw your 45-degree line. And that's the first step. The first step is to plot your graph, plot the equilibrium curve, and get the 45-degree line. The 45-degree line will be joining from the origin to the upper point here. So that is a 45-degree line. So that's the first step. The second step is to get your enriching operating line. Your operating line is based on this equation. Your enriching operating line is based on that equation. Okay, your textbook doesn't have this T over there. Yeah, doesn't have that. Your textbook only have it written R. Your equation is in this form, your textbook. That is your slope. The whole thing here is your y-intercept. What is your R? R is the reflux ratio, L over D. I did mention that earlier. Okay, what this is your mole fraction of component A in the distillate. So you jot it down there. Draw a vertical line until it reaches the 45-degree line. Okay? If you don't want to draw the vertical line, you should know that point is the point having the coordinate XD. Okay? So that's your starting point for your operating line. Your starting point will be here. That is your starting point for your operating line. To get a straight line, you need another point. What you can do is you can get the y-intercept. That's the y-intercept based on the equation here. That's your y-intercept. Does it include the minus sign? We will see in the example. Okay, so you get 2 points. That one point on the y-axis, and the other point on the 45-degree line, having the coordinate xd. So you join the 2 points, you will get your enriching line. So let's look at an example, how to draw it. This is the example. Scroll through the statement. You have a mixture of a liquid mixture, benzene and toluene. You're going to distill it at 1 atm. Your feed is 100 kilomole per hour, so I have got it here written 100 kilomole per hour, and it contains 45 moles fraction. Please jot down the unit. Take note of the unit, not jot down. Take note of the unit. It is mole percent. It's not mass percent. If the unit is given in mass percent, convert it to mole percent. Sometimes the lecturer like to play trick by giving mass percent. You have to change it to mole percent. The same goes for the flow rate. The flow rate must be molar of flow rate. Take note of that. Okay, your liquid, 45% of it is benzene. That means your component A is benzene. The other component, toluene, is B. So the rest will be toluene. That is the temperature of your feed coming in. So I have put it over there. That is your benzene. If you want to write subscript A, you can do so. If you don't want, it's understood that it is referring to benzene. The temperature of your feed is given. Okay? You're going to distill it until you get a distillate that contains 95 mole percent benzene. So your distillate will have that composition, 0.95. And your bottom product. Your bottom product will only contain 10 mole percent of benzene. So that's the composition of your bottom product. Okay, denoted by XW, your bottom product. Because the flow rate is W for your bottom product, and distillate having a flow rate of D, capital D. And so now the question asks, beside that, there's other information. Your reflux ratio is 4. So R is equals to L over D. That's the flow rate coming in is L. Okay? L over D, and that's equals to 4. Your average heat capacity of the feed, CP of the feed, is given 159 kilojoules per kilogram mole of Kelvin, per kilogram mole Kelvin. That is your unit for your heat capacity. It's not kilogram per kilogram, it's per kilogram mole. And the average latent heat of your feed is given 32,099 kilojoules per kilogram mole. Okay, so that's the information given. The question asks for calculate the kilogram per hour of distillates, kilogram per hour of your bottom product. You can do that easily because all you have to do is just do a metric balance on your column. So your total coming input equals to output. That's your balance. Output. Please write your basis. Your basis before this also you need to write your basis actually for the absorption. That's 100 kilomole per hour. That's your basis. Input coming in is F. Output going out is only the distillate plus the bottom product. So you know that your feed is 100. Your distillate you don't know. Your bottom product you don't know. One equation, two unknowns is not possible to calculate the unknowns. So you need another equation. So let's do a balance on component A. This is the total balance, is not this total balance. Component balance on component A, which is benzene, have F XF equals to D XT plus W XW. Going to copy, write it over there. Oh, there's not enough space. Don't have enough space there. What I'm going to do, okay. F is 100. The XF 0.45. Your D is the unknown. Your distillate composition, you do know it, 0.95. Your bottom product, the flow rate, you don't know, but you do know the composition of that bottom product. Now you have, this is your first equation, this is your second equation. From the first equation, you can come up with D is equals to 100 minus W. Okay, from the first equation, your distillate flow rate is equals to 100 minus your bottom product. So you're going to substitute that information in your second equation. Oh dear, I got this is equal sign. Okay, so now the only unknown left is the flow rate of your bottom product, which is W. You should be able to calculate that value. Let me look at the solution. Okay, from the textbook, the solution is 58.8 kilomole per hour. Once you substitute that inside the first equation, that's equals to 58.8, you will get your D. D is equal to 41.2, which will add up to be 100 kilomole per hour. So now you already know the composition of your output streams for the bottom and the top product. So that's done for the distillate and the bottom product. Next step is to calculate the number of theoretical tray or stages. That's what you need to do graphically. You need to do that graphically. Number of stages, theoretical stages or tray. And how to go about that? Let's bring our graph. Okay, I'm going to use my graph. I'm going to copy my graph. Here. That's my 45-degree line. Degree line there. Okay, this is the best I can if I'm going to do it on the same page. I get my 45-degree line. That's just the same that I did earlier. That's my 45-degree line. Make sure it's really, really on the origin. Okay. My coordinates, I have my XD, my XF, my XD unfortunately is, my XW is covered by the graph, but we know that XW is equal to 0.1. That is going to be my XW. That is my XD. That is my XF. I'm going to plot that. I'm going to locate that location on my on my graph. XW is 0.1. That's XW. My XD 0.9. Sorry, my XF, my feet mole fraction is 0.45. So 0.45. That's 0.5. That's my XF. And my XD 0.95. I need to locate these 3 points on the graph. Now, what I need to do now is get my point XD on the 45-degree line. So on the 45-degree line, well, that's somewhere there. That is my starting point for my operating line, enriching operating line. So just now the equation, I need to copy the equation. That's the equation just now. That's the equation. Yeah. Given the fact that R is 4, based on the equation, R is given 4. So substituting it inside your equation, as R, you don't worry about the subscript D there, but this one still maintain. Don't cancel it. That is the D, the R, the refract ratio with the D is the one that you need to cancel the D. Okay. Your R is equals to 4, so I'm going to put 4 there. 4 plus 1, X. Don't worry about this subscript. Minus the XD 0.95. 4 plus 1. So do the calculation. That is your enriching operating line. That is your y-intercept. That is your slope. That's your slope. That's your y-intercept. What you got to do, either you start from this point, that point, get your slope and draw a straight line, or the easier way for me is to use the y-intercept. The y-intercept is 0.9. 0.9 is there. Okay, so now I have 2 points that I can connect and get myself a straight line. So that will be my operating line, my enriching operating line. So let's do the line. Okay, so that is my operating line for my enriching section. That's done. Any questions so far? If you calculate the slope, it should be the same as 0.8. It's easier just to connect from the y-intercept to the XD coordinate on the 45-degree line. Any questions? Are you guys with me?
Yes, doctor. Doctor, for the y-intercept, the negative, we just ignore the
Yeah.
the
Yeah, you don't worry about the negative sign, because the negative sign will give you a lower than 0 points. I mean, below the origin. That's not what we want. We only have everything must be positive. Yeah.
Oh, okay.
Any other questions? No questions? Okay, next. What you need to get is your Q line, the fit line. Okay, the Q line is the fit line, or the Q operating line. And how to go about that? We'll look at the equation. Now let's see. That's the equation for the Q line. We have done the operating line, step number 2, for the enriching section. We've done that. Now we're going to get the Q line. What is Q? Q is defined as the fraction of the feed that is liquid, that is in a liquid phase. Okay? Q is defined as the fraction of the feed that is in a liquid phase. And it is also defined according to this statement. And also according to this equation. So if you use the equation, you will come up with this operating line for your Q. That is your Q operating line. And over here, you get that, you change it into equation, that is how it's going to be. Okay? From the statement, Q equals to mole to vaporize 1 mole of your feed, your liquid feed, divided by the molar latent heat of vaporization of the feed, you will get that equation. Okay, over here, let's go through it. That is your heat capacity of your feed, liquid feed. That is your heat capacity. That is the latent heat of your feed. I did not write that down, so please write it down in your notes. Okay, latent heat of your feed. This is the boiling point of your feed. That's the boiling point of your feed. Okay? And that's the temperature of your feed. The inlet temperature of your feed. Okay? So you can use this equation after you have managed to calculate your Q. Again, this is your y-intercept, that is your slope. There's a minus sign there. To calculate, to draw your Q line, you have your operating line. This is your operating line for the Q line. To calculate Q, you base on this equation. That's how you calculate Q. That is the composition of your feed. Now, let's tidy up because I need to calculate my Q first and then draw my operating line. Copy these two equations. Bring it over to the example. That's my equation for Q. Okay, so if I look at this equation, the first equation, like Q, I'm going to erase this equation because I already got it done. I need space. It cannot go there because there's a page break there. Okay, Q. Let's put in the value. 1 plus the heat capacity of your feed is already given. That's the heat capacity of your feed. Make sure the unit is the same, yeah, so that it can cancel off. Yes, kilojoules, kilogram, mole, Kelvin. So I think it's not a problem to cancel off the unit. 159. The boiling point of your feed you don't know, but the temperature of your feed is there. It's in Kelvin, so the boiling point should be also in Kelvin. Your latent heat of your feed is given. Now we need to find the boiling point of your feed. Your feed composition is 0.45 benzene. So what you have to do is you got to go to the temperature concentration graph. Okay, over here we have temperature on the y-axis, and you have your benzene mole fraction either in the liquid phase or in the vapor phase. So let's try to get our temperature for the boiling for the feed, the boiling temperature which is on the saturated liquid line. The boiling temperature is on the saturated liquid line because this curve is for the bubble point. That is the boiling temperature. Okay, so your feed initially is at 0.45. The composition is 0.45. So get that on the graph, 0.45. So let's draw a straight line from that point. If we intersect that straight line, that really straight vertical. It's not vertical. Okay, there you go. Okay, now that's your straight line at the composition of 0.45 roughly. Trying to get it exactly on that. Okay, there you go. And when it intersects with the saturated liquid line, which is the boiling point temperature, the boiling point line, the bubble line. So now you have to draw a horizontal line to get the temperature of your feed. Is that really straight? Is that really vertical? Sorry, it's straight, but it's not. Is it vertical? Yeah, it is vertical. No, sorry, horizontal, not vertical, horizontal. Okay, roughly that temperature is about, what temperature is that? 94? Something like that, you see. But over here, that's 95, 800, that's 90. Maybe 93.5, something like that, but give it a rough estimate. So if it's 94, now that's the boiling point of your convert your feet. 94 now. Change that into Kelvin. You need to put it into Kelvin because the equation, the temperature that we substitute inside the equation is in Kelvin. I really need to jot down the page number. I'm scrolling down. It's not a good thing. What page is it? Yeah, this is the page number. What page is it? It's 15. Okay. That is 95 plus 273 Kelvin. Did I say 95? It should 94, isn't it? Initially we got it 94. Yeah. So from there you should be able to get your Q and then substitute it inside this equation. So let's do the calculation. Okay, so almost time, but let's try to get this done. We will continue after the break. Got 1 plus 0.1952. So answer for Q is equals to 1.01952. I hope you guys also get the same thing. Now we substitute it here. Oh dear, what I'm trying to do. There should not be a 0 there. XF is the mole fraction of your feet. Your XF value is that value, 0.45 divided by 1, and it's 1.1952. So this is your y-intercept. That is your slope. So let's look at your y-intercept. Obviously, your y-intercept is going to be negative because the denominator is going to be negative.
You would just rip it off.
That's going to be negative. Your slope is going to be negative 6.13. That's the slope. So your slope will be positive. How to draw your graph? You have two ways of doing it. Either use the slope or use the y-intercept. So now, starting from your XF, this is your XF, 0.45. Get it on the 45-degree line. 45. Oops. One, two, three, four. That is your roughly. That is the XF on the 45-degree line. So you can use the y-intercept. If you use the y-intercept, it will be negative. So you will project downward here if you want to get a negative. You can measure 2.3 roughly. Let me try to do that. 2.3, the distance is 2. That's 2.3 somewhere there. 0.3 somewhere there. Okay, that's the y-intercept. 2.3. But it's not positive, it should be negative. So that's the distance, 2.3. The 2.3 is this distance. 2.3 is that distance. Okay. That's the distance. And you will project it downward. Same distance. I'm using because I'm using this I'm using my iPad, so it's easier for me to know the distance. It's not that difficult because I can just bring down my line to that point. So it's not that difficult for me. So if you're using iPad, it's not that difficult. I mean, you have your iPad, but if you're going to use it graph paper, then you kind of use your ruler. So this is my line, negative. Problem is I need to get it straight. Okay. So now this is going to be my point, my y-intercept, negative 2.3. So I have 2 points now. One of it is on the 45-degree line. The point is here at the bottom. So I'm going to connect the two. I'm going to get myself a straight line first. I'm going to project it until it crosses the enriching line. There it crosses the enriching, enriching operating line. Where it intersects is this point. Let me, where it intersects is that point. So that's one way of drawing your Q line. This is your Q line. That's one way by using the y-intercept. This is your y-intercept. But the other way is using your slope. This is your slope. If you use your slope, you start from this point. Let me highlight it. You start from that point and try to get another point. You should know how to do that. But let's put one value for x. Okay, let me explain it here. Slope is equals to delta y or delta x. You do have 1 point. Your point is here y minus y, x minus x. So your first point that you have is your on the 45-degree line. So that is your xf. Your xf is on the 45-degree line. That is 0.45. So it should be the same for the x and the y. So in order to get your other point, you need to get that coordinate. That is equals to 6.123. So let's just try to calculate it. Let's say a value of x equals to what? 0.6. Let's x equal to 0.6. Yeah, so what is your y? Your y is going to be, that's a very big number, isn't it? Too big. Better not use 0.6 because 0.6 is too big. Why? Did I get it right? Come on, guys, check my calculation. 0.6 minus 0.45 times 6.123. Okay. I got something very weird. Anybody getting an answer for y?
I got 1.37.
That's it, 1.37. Alright, it should not be, isn't it? 0.6 here give you a value of about roughly 0.6 something. If you look at the line, the Q line, 0.6 is here, isn't it? Should be somewhere there. It's kind of weird. I'm not sure what mistake did I make. But I only know that the point that you start is here, that is 45. 0.45, sorry, 0.45. But if you want to get the slope your slope will be something like this. Isn't it? That is your slope. Yeah. That is your slope. Delta y, delta x. Slope is equals to delta y over delta x. You think that's right? I'm not sure what mistake that I made here, but somehow the value is not right. You can check what mistake I made there. Okay, so, but to get the slope, you just need to get delta y over delta x. Let's see, what was my mistake? Not sure. Anyway, we get back to that. But the way to do the slope is using that equation. That is your slope. Did I make a mistake in the calculation? Check the calculation. Did I make any mistake? Let me check the solution from the textbook. Yeah, the slope is 6.12. That's correct. Slope is correct. In the textbook is 6.12. That's correct. The slope is correct. I'm not sure what mistake did I make here. Why is it so big a value? Because we know that I already plotted the graph. I know that if I have x equals to 0.8, I will have something somewhere here. Isn't it? That point. So why am I getting too big a value here?
Doctor,
Yes.
can I add something?
Yes, please.
Our y-intercept is 2.3, not 0.23. So can it be plotted down there?
It's negative 2.3, isn't it? Negative. That's, oh, sorry. Negative,
It's
isn't it?
negative
Yeah.
2.3, negative 0.23.
Hold on. What's the value of your y-intercept? Calculate it, please. Calculate your y-intercept. What is that value?
The value is negative 2.3.
Yes.
But did our y axis is 0.1, 0.2.
Oh God.
So
Yeah,
it
just relax.
will be really down there, right?
Yes, that's too low down there. This is 0.23. Sorry guys. Sorry guys. That's wrong. So that line is wrong. This is wrong. This I did it 0.23. It's 2.3. It's way below. It's way below. Okay, thank you for pointing that out. So that line is wrong now. I should go very down to get that Q line. So my Q line is the wrong Q line. Yeah, I got to erase this. So now we're going to do it using slope then. Using the y-intercept is not a good idea because it's too way below the origin. It's 2.3. Thank you very much for pointing it out. This value is too far. It's 2.3. It's not 0.23. I thought it was 0.23. That's why I did this. I did this calculation there. Sorry, I made a mistake there. Thank you for pointing that out. So it's not 0.23. It's 2.3. So it's double the length of the graph. So it's not wise to do that. So let's do it using slope. But we do it using slope. So that means this value is correct. Sorry, that value is correct, isn't it? It's too big. 1.37 is beyond our graph because our highest value is 1.0. That is almost 1 o'clock. So I better hurry up. So let's find let's x because of something else, not 0.6. Let it be 0. Maybe closer to 0.45, 0.5. This equals 0.5. And what is your y then? That y. Anybody, can you come up with an answer?
Doctor, 0.756.
756. So that's roughly 0.76. Okay, your coordinate will be x is equals to 0.5. Your y is going to be 0.76. So that's 1 point. The other point is on the x on the 45-degree line. So 0.5, 0.76. 0.5, 0.76, that's 0.5 there. Yeah, so I better erase this. 0.7, 6, isn't it? Yeah. 7, 2, 4, 6. So that's 0.76. So where the two of them intersect? 0.5. There you go. There you go. So that's our point. That's our point. Okay, so now you have that point here. That is on the 45-degree line for the fit. So now you have enough 2 points that you need to draw yourself your Q line. Let me erase this. Don't need that. I have enough point to draw myself a straight line. So from the 45-degree line, draw a straight line. There you go. That's my Q line. Okay, thank you very much. Thank you for pointing my mistake. That's your Q line. Where does it intersect with your x-axis? Sorry, where does it intersect with your enriching operating line? That is the point of intersection, not the earlier one. This earlier one is wrong. Here. Need to get smaller. Okay. Okay. Now you have your Q line and your enriching line. This is your enriching line. Operating line. Yeah, so we stop here because we will not be able to cover it in just 5 minutes. In fact, it's less than 5 minutes, so we stop here. Any questions? Any questions? You already managed to get part of the we're almost done with the solution actually. Yeah, the next step would be to get the stripping line, the stripping operating line. After that, then you do your steps. So we are almost done. For those who's keen to follow this example, in order to get the stripping line, all you have to do is connect your intersection of the Q line with the the enriching line. Right, this is the intersection. This line and that line, that's the intersection. So to get your stripping line, you get it on the 45 degrees line, XW, connect these two lines. That will be your line. Any questions? After that, it will just be stepping your number of stages. But then you need to read this statement before you can proceed to do the number of stages. Any questions? Anybody? I hope it's very clear because this question is going to come out in your second test. Graphically, it's not difficult, but it's just time consuming. That's the problem. Graphically, to draw the graph, to do the solution, is not difficult. It's just that it's time consuming. Okay, guys, since there's no questions, thank you very much and have a good break, a week of break. We will meet each other in a week time. Do take care because there's another variant going on. Omicron, is it? That's the name of the new variant. I'm not sure much about it. I don't really know much about it, but do take care and enjoy your break. Okay, guys, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. You're welcome.